It's a great pleasure to speak. Of course, it would have been even nicer to do that in person, but I'm afraid this is going to take a while before we can do this again. Yeah, I should first say that this is a work in collaboration with David Poyato and Juan Soler, and I'm going to jump right into it. So what am I going to try to convince you? What I want to do here is take a type of agent-based model for biological neurons, and in particular to consider a network of biological neurons. Now, as you will see, what we can do so far is rather rough from the modeling point of view, but I will address that later on. And so what's the basic idea? The basic idea is we really want to consider a lot of neurons, right? And they are connected. They are connected by their synapses. So you can have a relatively complex topology of those connections, and that is going to be the big point in all of that. But because there's a lot of neurons, what I would like to do is derive some macroscopic behavior, right? So I would like to derive a relatively simple system of equations that could predict average statistical quantities over all of the neurons. And so this now fits relatively nicely within what is called the mean field limit, and I'll say a bit more about that later, which is something on which I have worked a lot myself in other settings. So this has already been used quite a bit. The big originality here is how the topology of the network of a neuron is going to interfere with basically any classical attempt that we knew before to derive this sort of mean field limits. And this is very interesting. So that's the point I'm emphasizing on this slide, right? Which is because there's a topology and because this is supposed to be very important for how a brain functions, right? Then we should not expect that those synaptic weights should end up being transparent from the point of view of the analysis either. So it's very satisfactory to see that they actually also play a big role in the math analysis. All right, so let me write down the prototype of the system that I'm going to discuss today. All right, so we're going to consider n agents, right? And the state of each agent is going to be represented by some vector xi. And I'll be much more explicit into what is exactly in that vector xi in the next section when I show you actual models for neuron dynamics. But this will contain things like the activation potential on the neuron, for example. And I'm looking at the somewhat very simple dynamics in the sense that the time evolution of the state vector xi, right, is given by the sum of 2x2 interactions between neurons, which fits actually relatively well with this idea of synaptic weights. So up to there, right, this would be a completely standard type of system. The big difference in all of that are those weights, those wij. This is where we put the topology of the neuron network, right? And so in particular, what this makes is there's a very natural interpretation of this type of model as a many particle system on a graph, right? So now I can just consider each neuron as a node on a graph. Then each xi is a state of the node, right? And the Wij are the weight, right, of the connection between the graph nodes of each edge. And I should say that during this talk, I'm going to assume that the weights are symmetric. Just make my life a little bit simpler, but we don't need that, okay? So everything I'm going to say would still remain valid for directed graphs, so non-symmetric ones. And you would just have to symmetrize the various assumptions like the one I put below. Okay, so that's our starting point. And then I have two key assumptions that will actually put me in what I'm going to call the mean field scaling. And those are relatively natural. The first assumption simply says that the degree of each node on the graph is bounded. And another way of saying that is you see that here there's a sum, right? So this assumption actually guarantees that this sum is always of order 1. Which makes a lot of sense because there's no particular reason why a given neuron should see a very large or a very small influence from the neurons it is connected to. So that I think is very, very reasonable. The next assumption is that individually, each one of whose weight is going to be very, very small. And if you take a limit, n tends to infinity, so number of neurons tends to infinity, then this should go to 0. And the logic here is I don't want any individual neuron to feel a particular attraction from another individual neuron. I want the interaction to be spread. I want it to be averaged out so that I do observe a mean field. Now, this, I have no idea whether it is true in all neural network or not. It's still a very generic type of assumption, and we're going to work with that. If you don't have that, then for sure you cannot observe directly a mean field limit. And the main question in all of this is, what can I say, again, about statistical averages of this system as the number of nodes, the number of neurons, increases and becomes very large. You could add noise, right, to this. I'm not going to do that again for simplicity, but it wouldn't change anything either to the analysis. Right. And so I mentioned repeatedly mean field so far, right? So let me explain briefly what is the classical mean field limit. It's again a many particle system, but the very big difference is now the particles are identical, right? Which means that the weights you see are all the same. And if the weights are all the same and I want an assumption like that, then the logic is to take them like 1 over n. And that's exactly the equation you have here. So this is a very special case of the system that I had written on the slide before. And there's a well-known process which dates back to Vlasov, actually, in the 1930s. And this is really put into a completely rigorous framework by McKean in the 60s, the 50s, and which consists in saying, well, here we can actually replace this discrete sum by a conditional expectation. And so then instead of this original system, what you get is a McKean-Vlasov process, right? Where here you see that I'm just taking the conditional expectation, right? So if f is the law of the process, that's what I get. And of course, if I have, if all particles are identical, right, then the law of each one of them should be the same. So this is it. And this can actually be made rigorous relatively easily if the interaction kernel is smooth enough. And it's a lot harder if the kernel is not smooth enough. I won't discuss about that. That could be the talk in itself, trying to do the mean field limit for singular kernels here. So I'll just bypass the question completely. You also have a PD point of view, right? The previous equation was still somewhat a stochastic formulation of the system. But of course, I can now, out of this, I can just write an equation on the law of the directly, right? And what I get is the Vlasov equation, which is a partial differential equation, and it's something that looks like that. And at the PDE level, a very useful way of formulating this kind of limits, and it's something I will be using. So let me explain it briefly, is to use what is called the empirical measure. And it's this μn that is defined at the bottom here of the slide. Now, the empirical measure is a very simple object. It's basically a rescaled counting measure. So the empirical measure of a set, right, just gives you the proportion of the number of particles that belong to the set. So it's very simple, and it's a very discrete elementary statistical description of the system. Of course, if the initial position are random, then everything is random, and the empirical measure is a random measure as well. But what you can do in this classical framework of the mean field limit is you can prove that this random empirical measure is actually very close to the deterministic limit f, right, that solves this equation. And you have explicit expressions, so you need to use weak norms. There's a bit of a technical part here because you have Dirac masses in the measure. So you need to use norms that fit. You can use plenty of them. I chose W-11. People like to use Wasserstein distances there. I just didn't want to spend the time to define them. So again, I bypassed it, but there's various ways to do the analysis here. But that is essentially the classical mean field limit. And what's very interesting is very obviously this should be completely different. And the system breaks the symmetry, right, that I have here. So even this first step has no particular reason to be true. And if now my agents are not identical anymore, then each should have its own law. There shouldn't be one law that applies for all the agents, right? And so when I'm writing a formula like that, which law should I be using? This is a very, very natural question. And this is something we will see. But a bit later, so now I'm going to go back to a bit of modeling. I just want to mention that there are a huge number of examples now of mean field limits, right? So initially, this had been derived for plasmas. And immediately Vlasov noticed that it also was applying to some problem in astrophysics, actually, because at some large scale, the universe is flat, so you can still apply Newton's dynamics, and then what you get is exactly this kind of systems and this kind of limits. But this has branched out into so many fields in the meantime. So those are just a few examples. But when I'm looking at all of this, you know, then again, I'm coming back to my original question: what is the role played by synaptic weights, right? And which is, right, this is a picture of parts of a rat's brain, and you see the complex topology of the network, right? You see how neurons interact with many other neurons, but not with everybody. it's a very intricate, complicated system of interactions that we have. And so if all of that was fitting within the mean field limits, why on earth, how do we explain that such a system is different from that, right? And this is an actual simulation of galaxy dynamics, right? And this is the classical Newton interactions for exchangeable identical particles. Right? And you see that here, the topology of interactions is so much simpler. So this is what we'll try to understand, both from a modeling and from a math point of view. And I'm going to start with soon with the modeling, but before that, I want to make the question as precise as I can, right? And because there's an obvious fact, which is to say, well, if I consider two systems and I change the coefficients, then I won't have the same solutions, right? But that's really not what I'm asking, right? Because those two systems, right, even though for fixed n I will have different solutions for sure, they, again, could still have very similar behavior for large n, very similar macroscopic behavior. So again, I want to emphasize here is one question that is going to be recurring is, can I actually approximate the large-scale behavior of a system with different synaptic weights by the large-scale behavior of a system with identical weights? That is the right question. All right, let me discuss a little bit of modeling. And I'm going to start with, so I'm going to discuss two types of models for neuron dynamics, which are both well known. And I'm going to start first with what is known as the integrate and fire model. And so let's look at the dynamics of individual neurons first. This is relatively simple. What happens here is the neuron has a membrane potential, and this membrane potential is going to increase, and it's going to increase relatively simply, right? Here I take very basic ODE. Again, you can add noise if you want. And then the neuron has a certain probability to spike, okay? That depends on its membrane potential. And once the neuron spikes, right, it fires, and then the membrane potential is brought back to zero. So that's a very basic dynamics, right? Potential increases, then jumps back, increases, jumps back at random times. Again, add noise if you want, that's not going to change very much. Another class of model for the individual neurons is for example, the classical Hodgkin-Huxley system. And there's a typo here. There should be an equal 0 in this line. This is an equation. Sorry about that. So this is again an ODE on the membrane potential, right? But it's a little bit more precise in terms of the biochemical aspects of the dynamics. And in particular, it considers several potential channels for the neuron, right? The potassium channel, the sodium channel, and the sodium channel can be activated or inactivated, right? And so depending on those values, right, how much the channel is open, then you have various terms that increase or decrease the potential. Sorry. And of course, the channel themselves can open or close. So this is coupled with another system of ODE on each of the N, M, H, right, that you see coming on here. All right. So at the level of an individual neuron, this is considered to be more accurate, and this is still super simple. There are much more elaborate system of ODEs and SDs that have been written to model the dynamics of individual neurons. So this is just to give you a rough idea. Now, of course, the question is, we're not considering just one neuron, we're considering the network of neurons. So how do we couple the dynamics of all of these? In the simple integrate and fire neuron, this is rather easy to formulate because the dynamics of the neuron are uncoupled until one neuron fires. Right? So each one of them follow the same ODE or SD on their potential on their own without seeing the other neurons till one neuron in the system has a spike. And when neuron I fires, what happens is it boosts the potential or decreases the potential of all the neurons that are connected to it. Right? So when neuron I fires, you look at all the neurons J that are connected to I, and you increase the membrane potential Vj by some quantity alpha times the connection weight, right? And the connection weight could be a positive if all neurons are, reinforcing each other, or negative if one neuron can try to inactivate another neuron. Okay, relatively simple. And for the Hodgkin-Huxley type of dynamics, what you're doing is relatively simple as well. You add into the equation, right, on the membrane potential, and there should be an I here, it's another typo, sorry. On the membrane potential of each neuron, you add a coupling term, right? With the difference between the potentials of all neurons that are connected to J. And again, here you see the synaptic weights. And at the level of neural networks, then the Hodgkin-Huxley is considered less accurate than the integrate and fire. And that's because here the interaction is continuous in time. And it builds up on the potential, and that is not considered to be biologically accurate. From a biological point of view, it seems that neuron really interacts when they fire and not, strictly speaking, the rest of the time. So even though integrate and fire models the neurons dynamics in a rougher way, for networks, people consider this model to be more biologically relevant. However, it is also much more singular from a math point of view. And so far, what I can do is I can deal with that. With Hodgkin-Huxley type of dynamics, I cannot yet deal with integrate and fire type of systems. And you see that here there is essentially Dirac masses in time, so there is an additional singularity in the dynamics. And that's basically what I just said. And in particular, yeah, let me emphasize here, the fact that the notion of spike is harder to define in the Hodgkin-Huxley type of dynamic, this is a bit of a problem. And I should add that, of course, at this point, this is still super rough, right? Even integrate and fires, neurons are cells, they are extremely complicated cells. So we should not claim that either one of those as as an accurate model that really represents well the dynamics of any individual cell into this, right? Let's remain careful. Now, another interesting question now, I keep talking about the synaptic weights. Can we have a bit of an idea on the scaling of those weights? Yeah, somehow, right? At least a rough idea. And so first of all, how many neurons are we talking about in the brain, right? Because I keep saying mean field limits, n is large, n tends to infinity, this sort of stuff. So how large is n, actually? It depends, right? Depends on which type of animal, which type of brain, whether you're going to look at the whole brain, whether you're going to look at only some part of it. But let's say we consider the whole brain for mammals, right? Then this is between 10 to the 8 and 10 to the 11, right? Humans typically have a little bit less than 10 to the 11 neurons. This is the, seems to be a more accurate number. So yeah, I think it's fair to say that n is indeed very, very large, right? And in particular, when I'm adding this on graphs, having individual simulations of that is probably out of reach. What about those weights? Well, in the human brain, right, you have an average of 7,000 connections per neuron. So if I'm assuming that this is more or less well distributed, which is probably not the case, then that means that the typical synaptic weight, right, should be of order 10 to the minus 3, 10 to the minus 4. So, okay, it's reasonably small, not super small, but reasonably small. And moreover, a very, very important point that I'm going to emphasize in all of this, this is a sparse network. You see that we are very, very far from being fully connected, right? If there are 100 billion neurons in the brain and you're only connected to 10,000, well, yeah, by definition, this is sparse. This is going to play a major role in the analysis and in how difficult the math turned out to be. So that's actually a very big point. All right. This might not be as accurate as when I wrote this slide the first time a few months ago. So let me discuss that. For a very long time, of course, any idea that we could have a sort of accurate description of the synaptic weights in a brain were, you know, science fiction. And for these reasons, there were many popular ways of taking the synaptic weights through various notions of random graphs that I'm not going to describe, right? This is actually changing, and I just found an article a month ago that actually gives the complete topology of the brain of a fly, with all the neurons and all the connections between neurons. This I thought would not be possible, but it turns out, you know, we start being able to do things like that. Now, that still doesn't give you the value of the synaptic weights, right? But at least it tells you whether they are zero or non-zero, and that is already super remarkable. So it might be that, you know, in a few years, we might be able to be a lot more precise as to what those Wij should be in this kind of modeling. And this is a brief review of the literature. So this is huge, right? Networks of biological neurons have been extensively studied well before I knew much of anything about neurons. So this is just a brief glimpse, right? I tried to divide it into various type of studies, focusing mostly on the math side. So there have been several results on mean field limits. Most of those, the one I'm citing here, at least for sure, and I'll be more specific in the next section, actually assume identical neurons. So they are not the type of mean field limits that I'm interested in. Then you have a lot of studies of the mean field limits, so all the macroscopic models that are obtained through these studies. And it's a lot of fun, and it's very complicated as well. So again, not going to go there. And trying to justify the kind of modeling that I've been discussing in this section is also a huge topic, right? And I'm just citing a few names. This, again, I'm insisting, is very small sample of all the literature so far. All right. So I mentioned that we did have some existing results on the mean field limit for non-exchangeable systems. And I want to discuss two types. The first one is, well, you might say it's a bit cheating, but it's a fun remark. And the remark is, there's at least one known case where you can start from such a system, non-exchangeable synaptic weights, and the macroscopic behavior is still described by the classical mean field limit, so you lose the weights in the end. And you need two key assumptions for this to happen. You need that the sum of the weights, right, so the degree of each node, are identical or close to being identical. So here I normalize it by 1. It could be any number, but it is a number that does not depend on the node. Right. And the second thing is you need to assume that initially the membrane potentials, for example, were identically distributed. And if you have both of those, then you lose completely the synaptic weights in the end at the macroscopic scale. Now, of course, this is not what we want, right? We want to derive more interesting models, not the same old. It's relatively easy to say that this is likely not applicable for the kind of systems we're interested in, right? There's no particular reason why the degree should be similar. And for sure, there's no reason in the world why the membrane potentials should be identically distributed. But they are independent, you know, maybe, okay? But identically distributed, no. Right. All right. Now we get into a little bit more math. Another type of approach is based on graphons. Now, graphons have been a very big thing since they were introduced by Lovash, in particular, sometime in the early 2000s. And they are a way to try to represent the limit of graphs. So that makes a lot of sense, right? If we have a graph that is larger and larger, well, let's use the one thing we have that seems to be working reasonably well at describing large-scale behavior of such graphs. That's the graphon. And let me explain a little bit how the classical graphon works. First of all, they apply to fully connected graphs. That's a big thing. And of course, that means we'll have major issues when going to sparse graphs. And we want sparse graphs. So to emphasize this, right, I rescale the synaptic weights. So my previous Wij now is a W bar ij divided by n, right? Which emphasizing that you see all of it. In that case, what you're doing is you define a graphon. So you take this discrete W bar ij and you build a continuous function out of it. And you do that in a very trivial manner. You add extra variables, right, psi and zeta, that are going to be in the interval 0, 1. And then you cut your squares, your 1 squares, into small squares of size 1/n, right? And you define your W bar n as piecewise continuous, and the value on each of those squares is given by W bar ij. So very, very straightforward as an idea. Now, on that slide, let me make a big assumption. Let me assume we know that this function converges strongly to some limit. And by strongly, I mean strong topology of some LP space. Here I put L1. Then I can write a mean field limit. And the mean field limit I get is I'm adding this extra variable, right? So instead of having a limit on the low, I'm having a limit on an extended low where there's this extra psi. And then it reads in a very similar manner to the previous mean field limit, except I have this extra kernel W bar. And that's where you see the trace of the synaptic weight that remains there. Okay. How do we get the macroscopic behavior of the system out of that? Very simple. You take this low, you take its marginal in psi, so you average it in psi, that gives you the macroscopic behavior. And there's a lot of results there. So I'm just citing again a few of those. All right. Doing this is actually technically not that hard, but it's already very interesting. So first of all, there's a very natural interpretation to the limiting system. I wrote a PDE. If you prefer, of course, you can use a Makin-Vlasov type of process, right? And there's various ways of formulating it. You can formulate it as you know, having extended state space, right? X, T, psi. Or you can keep the same state space and add an extra random variable to the system. So that you see that as a projection of a higher dimensional system. Or you can see that as taking a conditional expectation, which if you think of the graph as some sort of random object, makes also a lot of sense, right? So you have this hidden random variable that describes the structure of the graph, and you take the conditional expectation with respect to this. So the formulation makes a lot of sense. It's really close to what we would like to have. But coming back to this, right, there was this big assumption here. And it turns out that, and that's the big thing about graphon, you can completely remove this assumption in that setting. So if I assume that I have a uniform bound on my W bar n, right, so this rescaled object, then I will always be able to do this. And this is a combination of two key points. The first one is to use what is called as the cut norm. And I put the exact formula here. It's not really important. You should think of it, this is not a strong LP norm. It's actually the norm of a kernel seen as an operator from L infinity to L1. All right. And the second point is, well, there was something fishy here, which is, right, the I and J are just labels. And I can label the neurons how I want. And the problem here is then this is absolutely not intrinsic, because if I relabel, I have a very different function. Right? So when I'm starting to do that, there's a very natural question, which is which labeling should I choose? And this is where graphon theory comes into play. What it tells you is there is a relabeling such that the corresponding graphon is compact in that norm. So if you relabel well, you can be sure that after extracting a subsequence, the WN bar is going to be compact in the right norm. And then everything works. And let me bypass this. This is connected to what is known as a regularity lemma on graph, which was derived by Schmeredi. All right. What's the issue here? Well, the issue is sparsity. I want to work on a sparse network because that is what neural networks look like. So I cannot have the 1 over n here. I cannot have this rescaling. If I don't have the 1 over n here, this is not uniformly bounded. And so none of that applies. Now, there have been various attempts to extend graphons to sparse graph, but this is very, very hard. And I'll just mention the notion of dgraph that Lovash introduced, for example. This doesn't work well because you don't have such a broad type of convergence as what you have here. And so this creates extra assumptions that you cannot check. Instead, this is our new result. So I'm considering the same original system. Okay. And I'm just assuming the 2 bounds that I told you about from the first slide. Total degree is bounded. Each connection weight goes to 0. Then there's a notion of extended graphon such that we still have the same limit. Right? This is the limit that I had written here. But now the limited extended graphon is in this crazy space, L infinity of one variable with value measure in the other. And I'm going to discuss this space a little bit more in the coming slides. So we are very happy. You still have the same notion of limit. You recover the macroscopic scale, right? So this is nice. But there is a huge difference between being in this space and being bounded or being in an LP space. And that creates a much more interesting set of possible dynamics and a lot of math difficulties. And I'll try to explain both in the next 5 minutes. So let's do a few preliminary remarks, right? I said initially, I don't need the symmetry, right? I put it in because it was simpler. I don't need it. If you don't have symmetry, you need to add the extra assumptions, right? You see that here, I'm summing over each row. Well, you need to sum over the columns as well, and that needs to be bounded as well. And instead of having L infinity with value measure, now you have L infinity with value measure in one variable and in the symmetry, right? Okay. I am assuming in this theorem that initially the state of each neuron was independent, right? But I'm not assuming that they are identically distributed. Now, you could even do without independence, but then you get a really messy type of limit. So if you want a good reduction in complexity, if you want something that is easily solvable, yeah, independence is pretty important. Now, one first idea of the difference between this and the standard graphons is, well, you know what? It's not even clear in which sense the equation holds. Because if this contains a measure, and f is only L infinity, and it is only L infinity in particular in this extra variable, I don't have any additional regularity. How on earth are we defining this? This integral in zeta, right? And how is it defined? Now, this is actually relatively straightforward, so I'll have time to explain to you that, yes, this is still well defined, but it's an indication of the deeper technical difficulties that we are facing in deriving this sort of things. And final remark, right? The limit holds in the same sense as before. The empirical measure, its limit is given by the corresponding marginal of our extended law F. All right, what about the meaning of the limiting equation? All right, so first key point, this space here has several definitions. You can try to define it as the combination of the two Banach space, right? Or Banach and metric space, by putting weak topology on measure. This is not what we are doing. This would be more similar to the degraph approach by Lovash, and we try to avoid this as much as possible. So here I'm taking what I think is a simpler definition from a math point of view. This is the dual of a Banach space L1 with value in continuous function. That's it. And then I pick the corresponding weak star topology that is induced by this space. All right. And let me ignore the x variable here because they are not hard. So let me focus on those extra extended variable psi and zeta. What we want to do is define this quantity, right? So I want to define this integral, and I want then to multiply it by a function. And I want to define those quantities without any extra regularity on F. And if I can do that, my equation at least, I can define it correctly. I can say what it means. This turns out not to be very hard. So let's do the following, right? Based on our definition of the space, let's take a regularized version Wn of the graphon W, okay? So let's imagine I have a nice Wn bounded, symmetric, that converges weak star to W in that space. All right, then the original integral, there's no problem to define it, right? Because Wn is not a measure, it's at least in L1. So no problem. And then this integral converges for the weak star topology of measure because I'm using the symmetry, right? If I multiply this by a smooth test function, right, in psi, then now I'm going to say that Wn converges in L infinity of zeta with value in measure in psi. I'm integrating against a function that is continuous in psi, there's no problem. And then what I have is weak convergence in L infinity of zeta against the function that is fixed, and in L infinity of zeta, no problem either. So this integral, right, I have not multiplied by F yet. This integral converges for the weak star topology of measure. But now I'm using the symmetry again. Wn is uniformly bounded in that space. I integrate against an L infinity function, L1, L infinity, it works, no problem. So this integral, right, with Wn is uniformly bounded in L infinity. If it converges, well, even in the sense of distribution, then it converges weak star in L infinity. And now I go back to the original star, I have something fixed in L infinity, and I have something that converges weak star in L infinity. Perfect. Well defined. So you see the sort of games that we end up playing, and here again, it's extremely simple, right? And finally, I said I like very much this limiting equation, and I like it much better than the previous version with graphons. And I like the fact that I can put measures. So what is a typical example of our limiting extended graphon, right? Well, here's the first one. Dirac mass between psi and zeta. This is a perfect example of a function that is symmetric and that belongs to that space. Well, it's not the most interesting dynamics in the world, but what this does is it means that here you don't have interactions between neuron layers. So you should think that you have an infinite number of layers of neurons. Within each layer, all neurons interact with each other, but they don't interact with neurons of other layers. So what you would really have out of that, if here I put delta of psi minus zeta, what you would have is a sequence or a parametrized mean field limit, right? So again, not the most interesting, but already something we couldn't have with normal graphons. Much more interesting is something like this. Now I still have this notion of layers of neuron, right? And this extra variable psi, it tells me on which layer I am. And then what I can do is that if you're on layer psi, you will interact with neurons on a layer phi of psi for some phi that you choose. And so now I have a hierarchy of layers, right? Each one of them interacting with the next. And already there, the possible behaviors are extremely rich because, right, this series of interconnected layers from psi to phi psi, phi of psi, and so on, right? Well, it might be finite. This is, you know, phi as some periodicity, right? So phi to some power k is identity. But it might not be. It might be infinite, right? If phi has some ergodic property, then this is going to be extremely complex. This also fits very well, by the way, for deep learning type of neural networks, which I have not considered yet, right? But this really represents the series of layers that one is connected to the next. And of course, you can combine all of this, make things as complicated as you want. And I will finish here. So I think this is very interesting work because it demands minimal assumptions on the initial graph. Of course, there are still plenty of open questions, and I'm just going to emphasize two of them. First of all, what happens if K is not Lipschitz, right? So more singular type of interaction, and a very nice example of singular type of interaction are those integrate and fire models that I cannot handle so far. And can we do that? Because those, again, are much more realistic from a biological point of view. I'll stop here. Thank you very much.